Hello. Professor Bouman is traveling again, so he asked me to cover his class for today, and we start here. So I looked at his video for the previous class. So this is basically the page he left off in the previous class. And in the class, he started talking about the white points. And so basically that he mentioned the three primary functions for the white point about calibration, color consistency, and gamut mapping. And but as far as this course is concerned, he said that we will be primarily focused on the calibration, and this means that absolute scaling of RGB values required for calibrated image data. This determines the color associated with RGB. So basically, my understanding is that suppose we are given the RGB value of the image data, then actually, these three numbers doesn't really tell us what exactly the color will look like, because in some sense, this RGB value is really locating a point in a coordinate system that is unknown to us, and unless we have some more information to specify this coordinate system, then this RGB value doesn't really tell us the specific color coordinate. So we need some more information, and one piece of this information is basically the white point. So my understanding is usually like you kind of fix the origin of this coordinate system. So you also will need several other pieces of information like the color of the three primaries. So, but anyway, so for the three items here, we basically focus mainly on the calibration, and we will have some more examples later on to talk about what this means. Defining white point. So when we talk about white point, this is basically we are choosing a particular light stimulus and call this a particular white point. And the way we a full specification of the white point is basically you specify this power spectrum of the light. So we have like a IW lambda here. So there can be several commonly used white points. So and the full specification of each will be given by power spectrum. So, but in many cases, we basically don't worry too much about the power spectrum, and we worry actually more about the color of the white point. So we can use the x naught, y naught, z naught, basically the color matching function of the CIE XYZ standard. So we can, if we know about the spectrum of your white point, then we can substitute this spectrum to the integral here to compute the XYZ tri-stimulus values of the white point. So this would give us a kind of a simpler specification of the white point. And sometimes we don't even need to know about the XYZ tri-stimulus value. So we may even specify the white point using the chromaticity value of the white point. So if you recall from previous classes, this is basically given by normalizing the tri-stimulus value so that they will sum to 1. So, but one point which is important to make here is that as we go from the top to the bottom, we are basically simplifying the way that we specify the white point. So the transformation, if you have the power spectrum, you can compute the XYZ, and then you can compute the chromaticity. But this, each of these two transformations is basically non-invertible. So if you got the chromaticity, you can't really tell what exactly will be the XYZ coordinate. And if you have the XYZ tri-stimulus values, then you still cannot tell the exact spectrum of the original white point. So this is kind of something important to know. Here we talk about several. So there actually have been several very commonly used white point standard, and 3 of these are the so-called eco-energy white, the D65 illuminant, and the C illuminant defined in NTSC. So the first one, eco-energy white, is basically defined by the power spectrum uniformly equal to 1. So that would match. So we define the eco-energy white using this uniform power spectrum. And if you recall, the color matching function of the usually normalized to 1. So if you compute the XYZ tri-stimulus values of this eco-energy white, what you will get will be basically the 3 values, 1, 1, 1. And if you normalize the 3 values, you got the chromaticity equal to 1/3, 1/3, 1/3. So the D65 illuminant is defined by the spectrum that I think some color scientists actually perform an experiment under the natural sunlight, and they measure the power spectrum over a range of wavelength. So they define this power spectrum, and again, if you use the color matching function of the XYZ, CIE XYZ standard, then you got the chromaticity 0.3127, 0.329, 0.3583. And the C illuminant is, I think it's kind of, can I call this kind of artificially defined? So they don't really have a well-defined power spectrum, but they defined this illuminant by specifying the chromaticity of the white points. Well, anyway, so if you look at all these white points, all the chromaticity are kind of close to 1/3, but they are slightly off from 1/3. And if you compare D65 and C illuminants, maybe the D65 will be slightly reddish, and C illuminant will be slightly bluish. And the comments here are that eco-energy white seems to be a more lateral definition, but this actually not very commonly used. C is for the original standard NTSC video. D65 is actually the much more dominant standard for white points these days, and although it is defined based on the lateral sunlight color, but people also find that this color is very close to the color temperature 6500 Kelvin. So this is basically where the D65, the name where you come from. So this diagram just gives 2 examples of the power spectrum of 2 different light sources. So the one over here is the power spectrum for D65, and the second one here would be the power spectrum for fluorescent illuminant. So so if you look at the x-axis, horizontally, this is the wavelength. So on the left-hand side is basically higher frequency corresponding to blue color. The right-hand side corresponds to the red color. So D65 will look slightly more bluish than the fluorescent color, fluorescent illuminant. Is that okay? Eco-energy white. So we previously mentioned that the eco-energy white basically have a spectrum equal to 1 uniformly. So given that, I believe the RGB here will be probably will be the CIE 1931 standard. Maybe. Let's think of RGB the color matching function of some kind of standard, whatever they are. But usually we will normalize the area the color matching function to equal to 1. So if you use the equal energy white power spectrum, and then we can compute actually the tri-stimulus values according to this color matching function, and whatever they are, they will be this integral basically will equal to this integral because I is equal to 1. So whatever they are, they will eventually what you got will be 1, 1, 1. So typical waypoint. So I think this slide basically is assume that R linear, G linear, B linear are data computed based on the equal energy white here. So let's say we have the data based on equal energy white, and let's say we want to compute the data based on another white point, let's say D65, for example. Then the RWP, R white point, G white point, B white point are the RGB value for our desired white point. So you basically compute these numbers using the same set of color matching function. So suppose we have the data computed according to the equal energy white, and we want to know the corresponding data that we can obtain if we're using the D65 or some other desired white point. Then we basically have to do this kind of normalization. So the R linear normalized by the R white point, G linear normalized by G white point, and B linear normalized by B white point. So this is some kind of converting from one white point to another white point. But an important point to make here is that when we are doing this kind of normalization, we need to make sure that all these RGB values should be in the linear energy space. So if your data has been gamma corrected, then you have to inverse the gamma correction before you do this kind of white point correction. And if you actually need to do the right gamma correction of your result, then you have to do the normalization first, and after that you do the gamma correction. So you should not change the order of doing these two operations. So we will talk about some examples about the calibration of using the white point. But before we go into that, we also need to talk about a little bit of the RGB color primaries. So here are basically three kind of popular primaries defined by different standards. So the first one is defined by the NTSC, and the second one is defined by PAL, and the third one is BT709. I believe it's the first two basically are standard for television broadcast. But I'm not quite sure, but probably this may not be true. But BT709 is a standard for high definition television. Would that be true? It's also the sRGB. sRGB, okay. So this slide basically lists the chromaticity of the NTSC primary. So if we are talking about the red primary of NTSC standard, we are actually talking about this 0.67, 0.33, and 0 chromaticity. And so you recall that the chromaticity has to sum to 1. So you usually will be specified by only the x and y coordinate. And from these two numbers, you can actually compute the z coordinate. So for the first case, you sum them up, you will get 1, and then the z coordinate will be equal to 0. And for the second one, you got 0.92 if you sum the two coordinate. And 1 subtract 1 minus these two, the sum of these two numbers, you got like 0.08. And for the last one, we got 0.78. So what? So we talked a little bit about the primaries, what we mean by equal energy white. So the part of the focus here will be we need to transform from a particular coordinate system back to some kind of XYZ coordinate system. So because XYZ is very commonly used as kind of a hub for color interchange. So let's say I believe previously we talked about some examples. So if we have many different devices, the different devices will have very different kind of native color space. So if you're using a camera to capture an image, so the RGB value, somehow you have to convert it so that it will be printed, for example, printed in a printer. And we want to ensure that the printer output will look very similar to what you are capturing from the camera. And because the two devices will have very different color coordinate system, native color coordinate system, we need to do some kind of transformation. And if you have many devices, then you trying to convert from each device to any other device would lead to a huge number of different transformations. So what people usually do will be they will first convert from one device to kind of more like a hub. So it's like people usually XYZ is how can I say like so XYZ is a absolute color system, and it covers the whole color gamut. Is that true? So the whole chromaticity diagram falls within the coordinate system of XYZ, and for many reasons, actually, people use XYZ as a kind of a standard for color interchange. So what people actually do will be they convert from one color coordinate system to the XYZ, and from this XYZ, they try to convert the color back to the second device color coordinate system. So in that sense, then you can convert from one device to another device much more easily. So, but anyway, here the focus is, let's say we have a color coordinate system. So we have NTSC color primaries with equal energy white point. So our goal is basically we want to find the transformation to convert data based on this color primary and white point to the standard XYZ coordinate system. And and this transformation basically will be a linear transform. So if you have the inputs of three-dimensional, output three-dimensional, so this matrix would be something like a 3x3 matrix. And what we need to do is basically to find what this 3x3 matrix M. Okay. So the way that we try to find this M matrix is the following. Now, so the first thing that we need to be careful is that the data has to be in linear energy space. So this point will be very important because XYZ is also in linear energy space. Now let's say so this will be the data from the source color coordinate system. Let's imagine that these three values will be equal to 1, 0, 0. 1 R equal to 1, G equal to 0, and B equal to 0. Okay, so now if we perform this, we don't know the matrix M at this point yet, but let's say we know about it and we perform this multiplication. So the 1, 0, 0 times M multiplied by 1, 0, 0, then the result basically will be the first column of M. Right. So if we have 1, 0, 0 here, the right-hand side basically will be the the first column of M. But if you think about it, 100, this particular color would correspond to the R primary of the NTSC standard. So in the previous slide, we say that, so this is in the previous slide, we mentioned that the chromaticity of NTSC would be something like these 9 numbers for RGB. So if we have the data equal to 100, then the left-hand side would be the XYZ tri-stimulus values of the R primary. So we basically, the result of that matrix multiplication would be something like a scalar multiple of the chromaticity of the R primary. So, okay, so this is the, so the chromaticity basically is 0.67, 0.33, and 0. So what we would expect is that if you put 100 here, the left-hand side should be a constant times the vector 0.67, 0.33, and 0, which is the chromaticity of the red primary. Do you understand what I mean? So is it clear? Okay. So by a similar argument, let's imagine that if we put 0, 1, 0 here, and if we perform the matrix multiplication on the right-hand side, then what we got will be the second column of M. And because the result should be the XYZ tri-stimulus values of the G primary, so this result will be a scalar multiple of the green primary chromaticity, which will be something like 0.21, 0.71, and 0.08. And we also will have the same argument for 001. So essentially what we are talking about is that this M matrix will be, first of all, it is a 3x3 matrix. And the column will be scalar multiple of the chromaticity of the RGB. This is shown here. So M will be 3x3 matrix. So each column, the first column basically will be a scalar multiple, a scalar number times the chromaticity of the R primary. The second column basically will be a scalar multiple of the G primary chromaticity. And the last column is another scalar multiple of the B primary chromaticity. So you can also write it in this particular form. So the first matrix are the chromaticity values of the 3 primaries, and we have a diagonal matrix alpha 1, alpha 2, alpha 3 are the scale of the 3 primaries. So this argument basically we come to this form of M, and what we eventually need to finish is basically to know the value of alpha 1, alpha 2, and alpha 3. So the color primary basically gives us this form of M, and another piece of information we have not been using is the equal energy white points, and basically this equal energy white point will give us. So we have 3 unknowns here that we need to find. So basically we need to set up 3 different equations to find these 3 unknowns, and two of these equations will come from the white point chromaticity, and we need to set up still another equation to find the third unknown. So okay, we got this form of M. And now, let's say we consider the RGB value equal to 111. Okay, RGB value equal to 111. Then if we multiply this RGB value by M, then we got something like this, the first matrix times the vector alpha 1, alpha 2, alpha 3. But we can also think about it, if the RGB value equal to 1, 1, 1, then the XY, the left-hand side should be the XYZ coordinate of the eco energy Y. And given that we know that the eco energy Y has chromaticity 1/3, 1/3, 1/3. So this XYZ coordinate would have to be some a scalar multiple of the 1/3, 1/3, 1/3 vector. Okay, so when we use this eco energy Y point, it basically provide us the two equations, and we still need to specify the third equation to try to solve all the alpha values. So what we usually do is basically we choose a particular scaling beta in such a way that the luminance value of the XYZ coordinate of the eco energy Y to be equal to 1. So the result of this would be the XYZ coordinate. We look at the second coordinate, which would be beta over 3, and we basically normalize this number to 1. So we chose beta to equal to 3, and so we got this 1, 1, 1 equal to m times 1, 1, 1, which is the second line. So if we solve this linear equations, then we got something like alpha 1, alpha 2, alpha 3 equal to 0.9867, 0.814, and 1.1985. Is it okay? And we can put these values back to the original form. Here, alpha 1, alpha 2, alpha 3, and then we can solve this matrix M. Would be something like this. So this matrix basically will give us the linear transform from the color coordinate system defined by the NTSC color primaries and eco energy waypoint to the CIE XYZ coordinate system. Okay. So here we have another example. We changed the source coordinate system slightly using the C waypoint instead of eco energy white. So again, if we have RGB data and we want to convert it the data to the XYZ coordinate system, then we need to find the matrix M. So because the waypoint is different now, so we would expect this M to be something different. So, but the strategy to compute this M is more or less very similar to the previous example. So again, the data has to be in linear energy space. We would, if we consider RGB to equal to 100 or 010 or 001, then you can argue that the columns of the M matrix should be proportional to the color primaries of the NTSC standard. So that essentially means, again, we're going back to this form of M. So because the primary are the same, so we got the same form of M, but the alpha 1, alpha 2, alpha 3 will be different because we changed the waypoints. Now, if we put the RGB value equal to 1, 1, and 1, then again the right-hand side will be equal to this form, the matrix given by the chromaticity of the color primary times the vector alpha 1, alpha 2, alpha 3. But on the left-hand side, on the left-hand side, we would when RGB equal to 1, 1, 1, then the left-hand side should be the XYZ coordinate of the waypoint, and this waypoint has to be equal to some scalar multiple of the chromaticity of the C waypoint. So this vector basically is the chromaticity vector of the C waypoint. And we would expect the XYZ tri-stimulus value to be a scalar multiple of this vector. So we have to choose a value here. And just for convenience, we just pick this scalar to be 1/0.001 316, so that the the luminance value of the XYZ coordinate will equal to 1. And so we also set up this linear equation system. You solve the value of alpha 1, alpha 2, alpha 3, and it will happen to be 0.906, 0.8259, 1.4327, and you just perform the matrix multiplication, and you got the result M here. Is that okay? So the next thing we talk about is this International Color Consortium, ICC. So it's basically a organization that set industrial standards for color management. So I actually looked up some information from, this is basically what you found from Wikipedia. So the organization is formed in 1993 by 8 industry vendors. And the objective is to create a universal color management system that would function transparently across operating systems and software. And they also have a motto of making color seamless between devices and documents. So from this, you kind of have an idea what they're trying to do. So the world is full of different kind of color devices, and they want these devices to work together in a seamless way. So this is what they're trying to come up with a standard to convert the color data between devices, basically, right? So in your notes, you mentioned that ICC Color Management standard will to use point-to-point transformation techniques to calibrate color capture and rendering devices with the best possible fidelity. The standard is based on Apple color sync system, so it's another color management system defined by Apple, and ICC is based on that. I just before the class I talked with Mark, but so is the color sync actually the basis of the ICC standard, or the other way around? Or?
Color sync's been out a long time.
Has been out in a long time.
Yeah, color sync was predated the ICC, and then the ICC was formed in a consortium of people that wanted to do similar things.
So basically, currently most of the devices will follow the ICC standards. So is that correct?
They use ICC principles, whether or not they follow the standard exactly.
I see. Yes. So the standard use color profiles for each input and output devices, and it also requires that each image file have an associated color profile. But most image file formats, so this is another point I discussed with Mark. He would suggest that this look may be a little bit outdated, because he thinks that most of the color file format actually today are supporting the ICC standard. So in your notes you say that most image file format do not support, so this may not be true, and difficult for non-professional use. So among all these items here, I actually looked up what exactly it means by color profile. So what I found is that you basically say something like attributes used to define mapping between some native color space to another color space, so-called the profile connection space, or PCS. And so this PCS will be either the CRE LAB or the CRE XYZ. So in the standard, it actually defines this PCS as kind of an interchange color space. So every device you want to follow the ICC standard, then you will have to provide some way to convert from the native color space to the PCS. So if your device has to cooperate with another color device, then what happens is this is actually a diagram Mark draw to me. So let's say we have a device 1, which may be some kind of cameras, and maybe we have another device 2, which is a camera. So suppose you use the device 2 to capture a picture of a scene. And when you go home and you want to print the picture using a very high-end device 3, which is a 6-color printer. So because the sensor of the camera would define some kind of a native color space, so the RGB values the device capture would basically have to be relative to the native color space of the camera. So we need to make sense out of these 3 values so that we can print the colors in a way that it looks similar to what we actually captured. So what happened in ICC is basically the device 2 will provide the profile, and in the minimum it would consist of what Mark told me would be something like a forward transform and the inverse transform between the color space of device 2 and the PCS, which would be either the XYZ or the CRE-LAB. So forget about this sRGB for the moment. So the device 2 has to provide this profile to contain the specification of the transform. And if you have your printer device 3, then similarly, this device will also provide the profile to convert between the PCS and the native color space of the device 3. So what happens is if you take a picture using your camera, then your computer can use this profile to convert from the data from the native color space of the device 2 to the PCS. And then you can convert from this PCS to the color space of your printer. So hopefully this transformation will not introduce too much error, and then the result will be reasonably faithful to what you captured. And so this is basically the mechanism how ICC standard work. And from what I learned from Mark, he basically told me that so the ICC defined the PCS profile connection space to be XYZ and LAB, but in practice the industrial leader maybe actually the Windows system and Apple system actually ignore this XYZ LAB, and they are more commonly using the sRGB as the PCS.
Well, one way of saying it would be they don't ignore XYZ and LAB. A lot of devices talk their interchange space is sRGB. So they understand that users don't understand LAB, they don't understand XYZ. They think in terms of RGB. So when you get a camera, what's the first thing you do is you display it on your computer at home, and then you hit print. And so if you're displaying on a computer that has an sRGB display, the assumption is you're converting from sRGB to your printer. Does that right make sense? So that's why a lot of, like Hewlett Packard, a lot of our printers will use sRGB as our color space to transform through. But underneath, inside the printer, everything's going through LAB or XYZ underneath. It's just we kind of hide that from the user.
Okay, so it's okay. So basically, but the basic mechanism would be so even though they in Windows, in other devices, they may talk through sRGB, but the basic mechanism would be very similar to the ICC standard. That's the main point, I think. So another standard coming out from the ICC, I think ICC, right, is this so-called sRGB standard. So it's a standard, industrial standard color space proposed by HP and Microsoft, but through the ICC organization. And
So this is referring to the simplification that I was talking about. This is the simplification. This sRGB standard is the mechanism by which devices can communicate in a simple way with some ICC kind of underneath it. So this is the basis for that.
Okay, thank you. So sRGB defines the standard color space for image in RGB formats. The standard basically specifies that the gamma correction should be gamma equal to 2.2, but he also, in your notes, Professor Bouman also put specifically that this is just an approximation. So for the moment, we can think of this gamma correction to be the power law that we have been talking about, with the gamma equal to 2.2, but we will talk some more later what this approximation means. So the actual gamma correction is not really the power law, but for the moment, let's think of it as a power law. So sRGB also defined the primary to be BT709 standard primary, and also the white point to be the D65 illuminance.
One thing you might want to add, prior to 1998, because this was around about 1998, you'd buy a monitor, and some monitors would have a 9500 Kelvin white point, some monitors would have 6000 Kelvin, some monitors would have 5000 Kelvin. So the problem is that anybody would buy a computer, and they'd set a computer up, and you could put 3 computers next to each other, and the same picture would look different on all 3. And the reason is because one's 9500, one's 6500 Kelvin, and the other one's 5000 Kelvin. So the whole idea behind sRGB was, let's try and standardize on what we think a standard viewing condition would be, which is 6500 Kelvin, the Rec 709 primaries with a gamma of 2.2. That's the gamma approximates the linearity of the display, right? And the perceptual response of the human visual system. So if you if everybody now manufactures a display that's sRGB, chances are you've got a much, much better chance of having the same picture look the same on more than one monitor. You know it doesn't work because if you look around this room, every single monitor is different. And we're all looking at the same picture. So even this doesn't work perfectly. But it's a lot closer than it was 10 years ago.
Thank you. So we have the standard sRGB. So one thing that we need to do is usually to convert between the sRGB and the CRE XYZ transmimulus values. So because sRGB is gamma corrected, so the way that we perform this conversion is that we need to first perform the inverse of this gamma correction. So we basically normalize the RGB value in sRGB to the range of 0 to 1, so you divide the values by 255, and do for the moment. So again, we put this approximate here. So the actual way to do this gamma correction is not this power law, but for the moment we think of it as a power law. So we do the inverse of the gamma correction, raised to the power 2.2. Then we obtain the linear energy space data, R linear, G linear, B linear. And one point that is very important to make here is that when we perform this kind of conversion, we need to make sure that this R linear, G linear, B linear should be stored and manipulated using the floating point precision. So, okay. Does that make sense? So you understand why we want floating point, right? So after we convert the sRGB data to the linear energy space, then we need to compute the XYZ through a linear transformation. So essentially, this basically means the same thing that we want to find the 3x3 matrix here, M. And you can actually look it up from some standard document, maybe But we will actually try to find out this M ends up to be something like this. But we will. So here the right hand side will be the transform times the sRGB data in linear energy space. And what we want to find is the XYZ. Eventually, we need to determine this matrix M. So this is basically very similar to what we discussed in the previous two examples. So this matrix M is a 3x3 matrix. So the columns of M would be proportional to the color primaries of the sRGB color space. sRGB standard, which will be the BT709 color primary. So we can just look up the chromaticity of the primaries of 709. Then we can put the So we can put the M matrix in a form like this, except that you have to replace this chromaticity value by the corresponding values from the 709 primaries. And then after we know that the form of the M, then we need to set up the equation to find the values of alpha 1, alpha 2, alpha 3. So on the right-hand side, we put the RGB value to be 111. If we put the RGB value to be equal to 111, then the right-hand side, M times 111 would be in the form of this. The 3x3 matrix of the chromaticity of the primaries times the vector alpha 1, alpha 2, alpha 3. And on the left-hand side, we would the XYZ value would be the XYZ value of the white point, which is D65. So if we check the chromaticity of D65, we got these three numbers, 0.3127, 0.329, 0.3583. So on the left-hand side would be a constant times these chromaticity values. A constant times a chromaticity value. So and again, we need one more equation to set up to solve all the three unknowns. So we basically choose this constant to be 1 over 0.2329, so that the resulting luminance value of this XYZ coordinate will equal to 1. And if you solve this system of equation, then you will got this M matrix transform for sRGB to XYZ conversion. So this summarizes again what we are going to do if we could have to convert from sRGB to XYZ. So we perform the inverse of the gamma correction, and then we use the M matrix we just computed to perform this linear transformation. And here, okay. Now we know, if we know this M matrix, we basically know how to do the forward transform from sRGB to XYZ. And this M matrix is you can actually compute the inverse of the M matrix. Is non-singular, so you can compute the inverse. So if we know the inverse of M, we can actually perform the backward transform. So which is done as the following. So if we have the XYZ data, we first multiply this XYZ data by the inverse of the M matrix. Then we got the linear energy space RGB data of sRGB color standard. And finally, we can do the gamma correction approximately equal to gamma equal to 2.2. And I think next time Professor Bouman will come back to discuss more about what exactly does it mean by this approximation. So the real gamma correction is not really the power law, so he will talk about it. Yeah, thank you.